So let's start with a simple introduction to what we mean by security and some aspects of what we desire if we want to secure a system and the mechanisms that we can use to provide security. And we're talking about security of computer systems, and we're going to focus on security related to communications across networks. Your computer science people, you're focusing on how computers and computer networks operate. We're not going to focus so much about physical security, the involvement of humans in providing security for systems. We're going to focus mostly on the computing side. Although the physical security and the policies that organisations need to provide security are important, we just don't have time to focus on them. Let's look at some introductory concepts. Some definitions. What is security? From textbooks or from some government standards that define security. The protection afforded to an automated information system in order to obtain the applicable objectives of preserving the integrity, availability and confidentiality of information system resources. So there's a definition of computer security. Maybe keywords in there that we'll need to explain in this lecture. What do we mean by preserving the integrity of the information sources, the availability and the confidentiality? Network and internet security. So this is more general about any computer system, but if we focus about securing information across a network, measures to deter, prevent, detect and correct security violations that involve the transmission of information. So now we're talking about sending information across some network. If there's some violations of the security of that transmission, we want to be able to deter people from violating our security mechanisms, prevent them, stop them from doing it. If they do it, detect that they're doing it, and fix the problem if they perform some attack or violate the security of our system. We're going to look at the ways that we can prevent and detect security and the different types of security violations and classify them. Coming back to those in the first definition, those three key terms of integrity, availability and confidentiality, they are key security concepts. Integrity, making sure the information, the data, is not modified when we transmit it across a communication system, as an example. If we have a message at a source entity and we want to send it to a destination entity, then when we send that message across our communications network, the message that's received should be the same as what was transmitted. If some malicious person somehow modifies that message during the transmission, then what's received is different from what is transmitted, and we've lost the integrity of that information. So that's one example of integrity of our information sources. Availability. A computer system has a purpose and a set of users and some intended use from those users. That is, if we have the Amazon website, that system, the set of servers, the website, is built so that people can go there, search for products and buy products. Okay? That's their business. And that system needs to be available to the customers. If the Amazon website is down for one day because of some security attack, that is, the system is not available to the customers, then that's a problem, because Amazon, the company, is going to lose a lot of money for lost sales over a period of 24 hours. So we want to make sure that a computer system and a communications network is available to the intended users. And one thing that you probably equate a lot with security is encryption and making sure that information is confidential. One aspect of security is I have a message, I want to send it to someone. I don't want someone else to read that message. I want to make sure the contents are confidential. So providing confidentiality is important. So 3 main concepts in security. There are others. So this has just come from one definition. Making sure that information is authentic. It comes from the person or the correct person. And making sure there's accountability in who's sending things and keeping track of what's happening in the system. We'll look into some of these in a bit more depth and define them. What happens? Accountability, to make sure that someone or something is accountable, takes responsibility for what's happening in the system, in the computer system, in the computer network. Okay, we have these concepts of confidentiality, integrity, availability. What happens if something goes wrong? We're a company, we offer some service to users. What happens if some malicious person breaches the security of our system? How do they impact upon different organisations? Well, 4 different ways. The breaches, the security attacks that breach the security of the system, can stop or reduce the effectiveness of the operations. SIT is an organisation. If there's some security attack, that means that, let's say, I prepare my exam before the exam and I store it on my computer, and of course I don't want students to access it before the exam. If for some reason a student can access the exam, and I find out about that, what happens? What's the impact on the organisation of SIT? The impact is on me. I now need to prepare a new exam. I'm going to waste another day or 2 to prepare a new exam. So it's reduced my effectiveness in my operations. I need to spend some more time doing a different exam, because now I know that the old exam is public to all the students. So that's an example of an impact on an individual, the same on an organisation. If some security attack on some company, then one thing that that company may need to do is to restore information, to redo things, and that reduces what they can do in their normal operations and eventually cost them money. There may be direct financial loss. If the communication system is computer system is part of a bank, and there's some breach such that some attacker can access the bank account of all the customers and take their money, then there is a direct financial loss to the bank or to the customers. So a security attack can mean a loss of money. Damage to assets. Physical damage, damage to computer systems, that is, if we lose data. We have a database and a security attack deletes all the data from the database. We've lost an asset, a computer asset in this case, or in some cases we may have physical damage to assets. You may have heard of Stuxnet. There was an attack on an Iranian nuclear facility, and some malicious software was introduced which resulted in failure of some parts of that nuclear facility. So the damage to the assets there, as well as probably financial loss and other impacts. And finally, in some cases, we can have physical harm to individuals. Maybe the nuclear facility, if the damage was much further and there was a meltdown, then that could be much more serious. And these may have different levels of impact. And organisations, when they try to assess security risks, they try to look at, okay, what impact may a breach have and at what level? Is it going to be serious financial loss or just a small financial loss? and try to classify the impacts of different breaches that may occur and look at ways to prevent and detect those breaches so that they don't happen, so that they minimise the impact. So that's a little bit about, okay, that we have some key security concepts. If something goes wrong, there may be some minor to severe impacts. Let's look more at the technical side and look at further definitions of what we mean by security. You know from data communications that well, you have heard at least that we looked at a 5-layer internet stack. There was another 7-layer OSI stack. And OSI actually focuses also on security. So ITU, a telecommunications standardization organization, has come up with some standard that says, what do we mean by security and what do we mean by security architecture? So we're going to look briefly at that just to get some of the concepts out. Because organizations need some way to design their computer systems to prevent security attacks and detect security attacks. So this standard defines some methods that they can use. How to define the requirements of security, requirements for security, and mechanisms to satisfy those requirements. That's what this standard, the X800 security architecture for OSI, talks about. It's a document or a set of documents that defines what do we mean by security and what are different mechanisms for providing security. We're just going to take some key terminology and concepts from this standard. The main aspects of security are attacks, mechanisms, and services. The attacks are what the malicious user or the malicious person or entity may do to try to violate the security of a system. The mechanisms are the things that we use to provide different security services. We're going to list the items in those 3 areas. Different types of attacks, mechanisms, and services. Just to differentiate, we often may talk about a threat or an attack. A threat is a potential violation of security. It may happen. There's a threat to my computer system, and it's possible that a student could get the exam. I would need to analyse that threat, see how likely it is, and see what impact it is to decide what mechanisms I would apply to prevent it. An attack is something that actually happens. So 3 aspects of security: attacks, mechanisms, and services. An attack is some action that attempts to compromise the security of information or facilities, the data, the information, or the devices. A mechanism, security mechanism, is a method for preventing, detecting, or recovering from an attack. We'd like to prevent attacks so they cannot happen. If that's not possible, we'd at least like to be able to detect if they do happen and then fix the problems that they introduce, recover from the attacks. So security mechanisms are methods for doing those things. Security service uses security mechanisms to improve or enhance the security of our informational facilities to stop attacks. Let's go through each of those in some more depth. Starting with attacks. Let's classify the types of attacks on a system into 2 types: passive and active. In a passive attack, we have a malicious entity, the attacker. If we do not have the malicious entity involved in some communication system or computer system, and we transfer some information, and then we introduce the attacker and they perform an attack. A passive attack is when, if we introduce the attacker, from the end user's perspective, nothing is different. They cannot notice. There's no change to the system because of the introduction of the attack. An active attack is when the attacker somehow modifies the system under attack, modifies the information, introduces new messages. We'll go through 6 different attacks. 2 of them are passive attacks, releasing the message contents, traffic analysis, and 4 are active attacks. And once we've gone through those 6, it should be clearer the difference between passive and active. We'll see that the passive attacks are relatively hard to detect. Because the attacker does not modify how the system behaves, it's hard to detect that the attack is taking place. So we need to prevent it, and generally easier to prevent. Whereas the active attacks, hard to prevent, but easier to detect. If they happen, we can detect them quickly. Let's go through 6 attacks, 2 passive and 4 active. Using examples here. And the example here, we're using a communication system. We have 2 users, Alice and Bob. They're the normal users in our system. They want to communicate across some communications facility, the internet, for example. And we have our malicious user, or our attacker, Darth in this case. Here's an example of if Bob is sending information to Alice, sending a message, and if Darth can somehow intercept that message in the communications network and read the contents of that message, when Bob and Alice want the contents to be confidential, then that's an attack on the security of the system, where we release the message contents. Bob has a message which contains the PIN number or the password for his bank account. He wants to send that confidentially to Alice, his wife. He trusts her. He sends an email with that password to the bank account. Darth intercepts the email, takes a copy, can read the email. Darth now has the password to Bob's bank account and can steal his money. So this is perhaps the most obvious or the most common thing we think about when we talk about encryption. Encryption is a way to prevent such an attack. Instead of sending the password in an email and allowing someone who intercepts that email from reading the contents, we would encrypt the password first and send it in an email, so that even if a malicious user reads the email, they cannot find the original password. They see an encrypted form. So we'll see how encryption can prevent this attack from working. But just one example of an attack. This is a passive attack because imagine Darth is not there. Then the normal behaviour is that Bob sends a message to Alice. From Bob's perspective, he sends one message. Alice receives that same message. When the attacker is introduced and the attack is performed, Bob sends one message. Alice receives one message. From their perspective, nothing has changed when there's no attack and when there is attack. That is, the attack has not modified the system resources in this case. And that's why we call it a passive attack. All Darth does is, let's say here we are in Thailand, here Alice is in the US. At some point in the communications network between the source and destination, maybe he finds a router. He works at an internet service provider and he finds a router and the email goes through that router. He configures some software to take a copy of that email and has it on his computer. But the email also goes through to Alice. So a passive attack in that case. Easy to prevent by using encryption. And we're going to spend a lot of time in talking about how encryption works. Encrypt the message before we send it, such that even though Darth can intercept, he cannot read and release the contents. Let's say we do use encryption. We encrypt the message. Another attack, a passive attack, is traffic analysis, where our malicious user, Darth, analyzes the information or the traffic going between the two users, and from that analysis can determine some useful information. Let's say, let's make sure we have some air. Let's say Darth and Alice are married, okay, husband and wife. And Alice has told Darth that she's at home, she's home in bed, Darth is out at work. But late at night, Bob, someone else, starts sending many messages to Alice. And in fact, Alice is responding, exchanging a lot of messages. At 2 a.m. in the morning, when Alice told her husband she's asleep, Darth gets suspicious that his wife is communicating with someone else, cannot read the messages that are being sent. They're encrypted. So they're sending messages using encryption such that Darth can see that there are messages going between the two, can identify the source and destination, but doesn't know what they're saying. Still, Darth can analyze that traffic and see, okay, my wife is communicating with someone at 2 a.m. She told me she was home in bed. He can then start to make some conclusions based on what's happening. And that's traffic analysis attack. The malicious user analyzes the communications and from that gets some useful information. They do not necessarily get the contents of the messages, but they get some information about that these two people are communicating, at what time of day, how often they're communicating, and so on. Maybe. So we need to detect either who is, or we can detect who is the source and destination of the messages. If this is an internet, then we can identify the source IP address and the destination IP address. And in fact, IP addresses can somehow give us some geographical, or can give us roughly geographical location. So we can get information about who is the sender and receiver. Another example is what, say, law enforcement may use. If this is a law enforcement agency and Alice is instead a known terrorist, and the law enforcement agency monitors who is communicating with this known terrorist, at what points of time, what days, how often, and perhaps if the communications with this known terrorist rapidly increase, then the law enforcement agency may do something about it. So that's an example where you cannot see the contents of the messages, but you can see that there are messages being sent and make some analysis and form some conclusions based on that analysis. Still a passive attack. How can we prevent it? We can try and hide the information. Let's say, firstly, we can try and hide who the source and destination is. One way we may identify the source and destination is based upon IP addresses. When my computer at home sends data to somewhere, the IP address of my computer is sent, or at least assigned to my modem. That identifies me. If I can go through some proxy device, then the person intercepting will think that it's coming from some other source and not necessarily from me. So if we can try to hide the source and destination address information, we can prevent or make this attack harder. Or if we can try and hide the messages in other messages. Let's say that really Bob only needs to send messages at 2 a.m. But that looks suspicious, sending messages to Alice only at 2 a.m. for 10 minutes. But if Bob sent messages to Alice all during the day, then it may not look so suspicious. So you can hide information and hide that certain things are happening by sending fake or unnecessary messages so that it's harder for the attacker or the malicious entity in this case to determine what's happening. Now, when I say the attacker here, they may not be a bad person. It may be a law enforcement agency, for example. But they're performing the security attack on the system. Passive, because without the attack, Bob sends a message, Alice receives a message. With the attack, Bob sends a message, Alice receives a message. No different then. Now let's look at 4 active attacks. First, the masquerade attack. Masquerade to pretend to be something else. So here we have Alice. Alice is the financial officer for an organisation, for SIT. She determines how much you get paid and so on. But she takes directions from the director. Bob is the director. So he normally sends directions to Alice saying, increase someone's salary by 10,000 baht or decrease by 20,000 baht. Darth is our malicious user. Let's say I'm Darth and I send a message pretending to be from the director or pretending to be from Bob saying, increase Steve's salary by 10,000 baht. When Alice receives this message, it looks like it came from Bob. And because it looks like it comes from Bob, she follows that message and increases the salary. But it in fact came from someone else. It came from Darth pretending to be Bob or masquerading as Bob. So there's an attack on the security of the system. It's active because with the attack, Alice receives a message. If there was no attack, Alice receives no message. If you remove the attack, in this case, Bob sends nothing, Alice receives nothing. Introducing the attack, Alice receives one message. Therefore, we consider this an active attack because it's modified the normal behaviour. The normal behaviour is nothing is sent. With the attack, there's a new message sent. And that relates to this cartoon from the front of your handouts. On the internet, nobody knows you're a dog because when you're communicating with someone, how do you know it's not someone pretending to be someone else? And that's why we need the security service of authentication. And generally on the internet, there's no authentication. We would look at how it can be provided. Replay attack. Finance officer, the director, and this is me, the malicious user. The director has sent a message to the finance officer, a valid message saying, increase Steve's salary by 10,000 baht. That's fine, that's normal. I intercepted that message, and 1 week later, I replayed, that is, I sent an exact copy of that message onto the finance secretary. So she receives a second message, increase Steve's salary by 10,000 baht, so now my salary has been increased by 20,000 baht. The director said increase by 10,000. I took a copy of that message, replayed it at a later date, and the receiver thinks that that second message is valid and increases my salary. So this is an example of a replay attack, because the message has been copied and sent as is, a copy of that, a replay of it, to the destination. Again, active attack. Modification attack. Here, the director sends a message to the finance officer saying, decrease Steve's salary by 10,000 baht. I intercept the message before it gets to the destination. I change the message. I modify it. I change the word decrease to increase. And then I send the message on to the finance officer, and she gets a message from the director saying, increase Steve's salary by 10,000 baht. Of course, the attack's been successful. The malicious user modifies the message contents between the source and the destination. Why is it active? Why is it an active attack? Yeah, the message has been changed. So something has been changed in the system. Still same number of messages, but without the attack, Bob sent message A, Alice received message A. With the attack, Bob sends message A, Alice receives message B. Something has changed there. It's an active attack. Last one, slightly different. We have a server, provide some service to the users, a website, for example. Normally, the users access the website and get some information or perform some operations. Our malicious user starts sending many messages to this server. As a result, the server becomes busy. And when the server is busy, the normal users cannot access it in the normal way. And therefore, by sending a lot of information or a lot of messages to the server, the attacker has denied the normal users from using the service. A denial of service attack. So this, yeah? Yeah, okay. No, so this one corresponds, we spoke about availability before. We have a communications system, communication service. We wanted that to be available to the users. A denial of service attack makes it unavailable to the users. Of course, if there's no attack, there'll be no messages sent. So this is also an active attack.
Why are you saying
Denial of service. That is, we're denying the service to the users, not Daniel. Okay, so we have, in general, 6 types of attacks. First 2, release message contents, traffic analysis, passive attacks. And the last 4, masquerade, modification, replay, and denial of service, all active attacks. And that's the 6 general types of attacks in a security system.
If they attack, why Alice not suspicious that she received twice message?
Why is Alice, in a replay attack, why is Alice not suspicious that she received 2 messages? Maybe, if we go back to our example of the director sending a message, maybe the director every so often, so many weeks, sends a message about the salary updates. Alice trusts, if it receives an email and the from says from the director, she trusts that and just reads the contents. Receives it at a later date, a later time. Of course, they were very simple examples that we used here. They can be much more complex how these attacks can have some impact on a communication system. Maybe on a packet level, not just an email, it may be an individual packet being sent that is replayed that can have some impact on a system. So a common question in an exam and in a quiz is list the attacks, 6 types of attacks, classify them as active or passive, and describe those attacks. So you should know about those 6 attacks and the difference between them. So that's about the attacks. What about the services that we provide to try to stop those attacks. Again, different organisations have tried to create definitions of what we mean by a security service. ITU said a service is that provided by a protocol layer, so it's about the communications protocol, that ensures adequate security of systems or data transfers. So some service offered by a protocol to make sure the data transfer or the computer system is secure. A very general definition. So it gives some protection to system resources, another type of definition. Some communication service or protocol service provided by a system to give a specific kind of protection to a system resources. Security services implement security policies. An organisation may have some policies about the security of their computer systems and computer network. They will use different services to implement those policies. One policy, let's say a policy of SIT, is that students cannot access exams before they're available. That's obvious. And for that policy, more specific, that faculty members cannot store exams available to their students on their computers. Maybe that's a directive from SIT, for the organisation. Or cannot store them in a form that is available to students. We may apply some security service to meet this policy. That security service may be to make sure that the exams, even though they're stored on a computer, are confidential in some way. So we'll see that one security service is providing confidentiality, making sure that no one can read the contents of that exam unless authorised to. And we'll see one mechanism that implements that security service is encryption. So we'll see that at the top, organisations or individuals have policies, how they want to be secure. We implement them with different services. We will list those services. And those services are implemented by different mechanisms. And we'll go through and list those mechanisms. And in fact, we'll spend most of this course talking about the different mechanisms. So here's a general, or what's generally considered as the list of the 6 main security services. Different people may divide them into 5 or 7, have slightly different names, but for this course we'll just list these 6 security services. Authentication. Making sure that the entity that we're communicating with is who they claim to be. If, let's say, the director sends a message to the finance officer talking about increasing or decreasing someone's salary, the finance officer wants to make sure that the message that they received actually came from the director, wants to authenticate who is the originator of that message. Because if they do not, as we saw, we can easily perform an attack where someone could send a message masquerading as the director, the finance officer will receive that, and we'd have an attack. Authentication is making sure that whoever sent the message is who they claim they are. That is, the peer entity, the other entity that we're communicating with, is who they claim they are, or that the data that we receive is valid and come from the correct origin. So making sure that who we're communicating with is who they say they are. It may be identified based on a person or based on a computer or even a piece of software. Access control. Prevent unauthorised use of a resource. So the resource is a computer resource, a network resource. We have a communication network in SIT. It's for SIT students and staff. We don't want people in a neighbouring factory to use our resources. to use our network, to access our computers and use our computers. So we want to have some access control that prevents outside people from using the resources within our organisation. The best example here is a firewall, and you probably have one at home. You have your internet at home, you have your computers in your home, you have a modem, possibly on the modem or on an individual computer, you have a firewall. That is providing access control. It's controlling who or what can access your resources. Data confidentiality, or simply confidentiality. Protect data from unauthorized disclosure. Make sure that people or entities that are not allowed to see the contents of the data cannot. Keep that data confidential. Integrity of the data. Make sure that the data that is sent or is stored is not modified along the way. If we send data across a communication network, what is received should be identical to what was sent. Maintain the integrity of that data. If it's modified along the way, then the data has not maintained its integrity. So we want a service of providing data integrity. That's one of our objectives. Availability, we've mentioned this. Make sure that the system is accessible and usable when needed by the intended or the authorized users. So Amazon's website, the intended users are anyone in the world, customers who want to buy products. So they have a website where you go to, you can buy products. They want to make sure that that system is always available to those intended users and that malicious users don't prevent that system becoming unavailable, i.e. some denial of service attack. Last one, number 5 here, non-repudiation. Make sure that entities involved in communications cannot deny those communications at a later stage. This is something like an electronic receipt. When you buy something in a shop, you get a receipt, and that's some way to identify that you bought or you paid money for that object. Some way to identify that. What about in communicating across the internet? Well, the same way, we'd like to have some receipt to know, to be able to prove later that we've purchased something or we've performed some communications across the network. And that's what non-repudiation service is about. Stopping people from denying that they've communicated in the past. Maybe it's not a good example, but if you send me your assignment via email, then you would like to have some receipt or some confirmation that I've received that assignment. Maybe you send it to a TA in a lab, and unfortunately the TA is a malicious person and they lose it and they say, no, I didn't receive your assignment, you didn't submit it. So that's a problem. So if you can have some evidence that you did submit it, then you could come to me as the instructor and say, well, I did send this email and therefore something's gone wrong. So we need some way to prevent people from denying that they've communicated in the past. So these are the 6 security services that we want to offer. Depending on the policy of the organisation or the individual, we will choose these services as needed. As an example, I want to send an email containing the exam to the secretary to print that exam. I would like to have data confidentiality in that case, because I want to make sure when I send the email that no malicious user, no student can listen in via the wireless network, get a copy of that email and see the exam. So I'd like to have confidentiality in that case. Possibly we'd like to have authentication, that the secretary, when they receive the email, they want to make sure it actually came from me and not came from some smart student who's creating a fake exam and they know all the answers to, sends it to the secretary, she prints that, and now the student knows that exam. So possibly we'd like the authentication service there. Depending upon what we think are the impacts of a breach, the likelihood of a breach. So depending on what we want to achieve, we will choose one or more of these 6 security services. The last part, so the 3 aspects, attacks, services, mechanisms, are the things that are used to implement those services. How do we provide confidentiality? How do we provide authentication? They are the security mechanisms. Most of the mechanisms, so there are many mechanisms, usually there's no single one that provides all services, but most of the mechanisms we see rely on cryptographic techniques, rely on some form of encryption to provide each of those different services. Some examples of mechanisms: encipherment, which is really encryption; digital signatures, access control, a firewall is a mechanism; data integrity is in fact a mechanism which can provide the service of data integrity; some exchange of authentication provides authentication; and different techniques or mechanisms are available for non-repudiation and availability and so on. We're going to spend most of our semester looking at these mechanisms, starting mainly with encipherment and the different cryptographic techniques, cryptography. This table simply lists some of the mechanisms and some of the services that they can be used to implement. We can use encryption and digital signatures to implement peer entity authentication. We use encryption or encipherment to implement confidentiality. And other mechanisms can be used as well. Just some examples there. So that's the main things we want to cover in the introduction. We have attacks, services, and mechanisms. You need to know the types of attacks, know the 6 services and the difference between them, and we're going to teach you about the different mechanisms. To teach you about those mechanisms, we'll use some common model of network security in our examples. When we're talking about providing security in a communication system in a network, we'll normally talk about the different entities and the operations they perform in terms of this model. This captures most aspects of network security. We normally have a message that we want to send, some sender, some source that wants to send that message, there's some recipient. So we want to get the message from the source to the destination. We're going to send it across some information channel, such as the internet or a link. And there's an attacker or an opponent who can access that information channel and access any information that's sent across it. That's the assumption that we'll make, that we have the source or the sender wanting to send a message to the recipient. We have the opponent or the attacker that can see anything that is sent across the channel. That channel may be a single cable, it may be the entire internet across the globe. What we'll do to make sure that the opponent cannot access that information, and also to provide things like authentication and other services, we'll normally perform some transformation on the original message, say some encryption, so that at the source we don't send the original message, we send a secure message which is taking the original message, perform some transformation and send across the information channel the secure message. That's received, the recipient performs some transformation such that they get the original message back. The opponent can see the secure message, but if the transformation is chosen appropriately, they will not be able to obtain the original message. And we can use this for confidentiality, but we can also use similar concepts for authentication and other services, data integrity as well. In addition, sometimes we'll have what's called a trusted third party involved. Someone that both the sender and the recipient trust. In case something goes wrong, we consult this trusted third party. Or if we need to share some secret information between sender and recipient, we may use the trusted third party. We'll see some examples of that in the next topic. So just a general model of the entities involved. Sender, recipient, attacker communicate via some channel which the attacker can access. That's what we assume. When we talk about access control and other services, this is a different model that we may have. We have our information system, our computer, our network, our resources. We have some channel that entities access those resources via. We have some what's called gatekeeper function, like a firewall that controls who accesses the resources and who cannot. It blocks whatever should not get access and so on. Just another model for the specific case of access control. Any questions? What we're going to do is talk about that cryptography now, how the cryptographic techniques can provide the mechanisms that we need and eventually provide the services. And we're going to start very simple. What we're going to do is introduce encryption, and we'll use what's called classical encryption techniques to demonstrate the concepts of encryption. Classical means old in terms of thousands of years in some case. Things that we do not use now for encryption, but the very basic algorithms will demonstrate what techniques are used now in the more complex realistic algorithms. So we'll go through some very old algorithms. Why? Because we can do manual calculations with these very simple ones and see how they operate in detail. But first, let's look at what we mean by encryption and another model for how we apply encryption. Some terminology. We saw in the second to last slide that we have some model where we send a message from source to destination. But in fact, we transform that message into a secure message. The terminology we'll use is that the original message is called plain text. We're going to encrypt the plain text, and the output of the encryption is called ciphertext, the encrypted or coded message. Encryption is the process of converting from plain text to ciphertext, also called enciphering. We'll refer to as encryption. And the opposite, when we receive a piece of ciphertext, the encrypted message, and we want to get the original plain text back, we need to apply decryption. So that's the process of restoring the plain text from the ciphertext. We'll use some information which is secret to the sender and receiver to perform the transformation. And that information, one part of that information we use is a key, normally a secret key. Some information that's known by the source and the destination, but is not known by anyone else. It's secret only between the sender and receiver. Cryptography is the study of algorithms used for encryption. A cipher is a particular algorithm. Cryptanalysis is the study of the techniques for decryption without knowing the plaintext, trying to break the cipher to find the plaintext. And cryptology is the combination of the study of the algorithms for encryption and how to break those algorithms. So here's a model of encryption. We take plaintext as input. We apply some encryption algorithm using a key, and we get as an output ciphertext. We transmit that ciphertext across our information channel from the source to the destination. So this is all happening at the source. The source has a plaintext message. They perform some transformation. They apply the encryption algorithm using the key, some information that they know. And then they send that ciphertext across the communications network. It's received by the recipient. The recipient decrypts using a decryption algorithm, using a key as input, and gets the original plaintext out as the output. That's the idea. We call this symmetric encryption. Symmetric in that both the symmetry in the keys, both the source and the destination use the same key in this case. Take the plaintext, encrypt with key K, send the ciphertext. The recipient takes the ciphertext, decrypts with the same key K. Same key as here. And we get the original plaintext. This is symmetric key encryption, or simply symmetric encryption. There's an alternative, which is asymmetric encryption, or public key encryption, where we use two different keys. We will cover that later, closer to the midterm. We're going to focus mainly on symmetric encryption up until the midterm, and all the classical ciphers we'll go through are using symmetric encryption. One key used by both the source and destination, and it's a secret key, a shared secret. Both the source and destination must know the value. No one else can know the value, especially the attacker. Otherwise it's not secret. That's the process that we'll go through. Some assumptions about what happens, or this model. First, for this to be successful, for it to be secure, such that the attacker cannot get the original plaintext, we need what's called a strong encryption algorithm. This encryption algorithm must be such that if the attacker can find the ciphertext, they cannot go backwards and get the plaintext unless they have the key. Here's the sender, here's the receiver, in the middle is the communication channel. The attacker can see anything sent across the communication channel. As the attacker can see the ciphertext. If the attacker has the ciphertext, they don't have the key, because that's secret, then a strong encryption algorithm is one such that it's practically impossible for the attacker from the ciphertext to determine the plaintext. If our encryption algorithm is strong, then the attacker cannot find the plaintext without the key. That's a requirement for providing security. The other one is that the secret key is known by the sender and receiver, and only the sender and receiver. It's secret. If someone else learns the secret key, it's no longer secret. So if you and I want to communicate, then somehow we need to agree upon some key. Maybe I'll write it down on a piece of paper, give you the secret key, and then I'll go back to my computer and send you a message encrypted with that key. If someone else finds the key, then the security of the system falls down, it fails. So we'll assume that the attacker does not know the key. We will look, when we look at cryptanalysis, how the attacker will try to determine the key. Some assumptions is that the attacker does know the cipher. They do know the specific algorithm being used. In this slide, there's an example, AES. AES is a name of an algorithm, an encryption algorithm. The algorithm is defined in some document. Everyone knows the algorithm, including the attacker. It's public to everyone in the world. So we'll assume that what happens inside here, the algorithm, is known by the attacker. It's public. And same with the decryption algorithm. Sorry. And we'll assume that the sender and receiver can exchange keys in some secure manner. In our example, I wrote it down on a piece of paper and I passed it along. Let's say that's secure and the attacker cannot see that piece of paper. So same in a communications network. If we say I'm using symmetric key encryption and I've got a key on my computer and the destination has that same key, we assume somehow that I exchange the key with the destination securely so the attacker cannot learn the key. After the midterm, we'll look at ways for distributing keys. There are different techniques for doing that. Here's the same system, but in perhaps a more mathematical formulation of our symmetric key encryption. And we'll see that often we'll use this notation when we write down the operations being performed. We have our message source, the source that wants to send a message, some message X. X is the plain text. We have a key or something that generates a key, the key source, the key K. That key needs to be known by the source and destination. Somehow, that key K is distributed from the source to the destination we show here by a secure channel. Some method that we're not going to be concerned how that happened, but we're going to assume that the source knows K, the destination knows K. Maybe they talked to them on the phone, maybe they wrote it down on a piece of paper, maybe they used another encryption scheme to perform that distribution of the key, but both sides know the key. We apply some algorithm. We can write that as a function. Some encryption algorithm takes as an input some key and the plaintext message X, and some function E that takes those as an input and returns as an output, what is it called? Y in this case. That's the encryption step, and it's shown here. The ciphertext, Y, is the output of encrypting plaintext X with key K. So it's just some mathematical way we can express these operations. What is the function E? Well, that's the encryption algorithm. And there are many different encryption algorithms. We send the ciphertext Y across our communications network. The attacker, or cryptanalyst, the entity that's trying to analyze and to break the security, can receive Y. They know the ciphertext. The recipient of the ciphertext takes the key K and the ciphertext Y and decrypts. They apply the decryption algorithm using the same key K, the received ciphertext Y, and they get the original plaintext X as an output. That's the recipient here, shown here. The intended receiver can calculate the plaintext if they know the key and if they have the ciphertext. Ciphertext is public, everyone knows it. Decryption algorithm is public, everyone knows it. Key is secret, only the source and destination know the key. What the attacker wants to do is, given the ciphertext, Y, so the attacker knows Y, the ciphertext. They know the encryption algorithm, that is, they know the function E. They know the decryption algorithm, D. They are all known to the attacker. They want to determine the plaintext. They want to make some estimate of what is the plaintext here. If they get that, then they're successful. And they want to and or they want to determine the key, because that should be secret. If they can do analysis from these three pieces of information to find the plain text, the system is not secure. Or if they can find the key, the system is not secure. So that expresses what the sender and receiver want to do, and also the goal of the attacker in this case. That's going to apply for all the algorithms that we will look at in this lecture. In your handouts, I don't know if I gave it to you, is there a sheet that explains the notation? I tried to, but yes? If it's not in the handout somewhere on the website, there's a single document that lists the different mathematical notation that we will use. We'll see more as we come. But when we go through examples, we'll often use this notation to shorten things. Let's see if we can get to some examples to finish off today. Too much talking. So, what the encryption and decryption algorithms do? How do they take the plain text and produce ciphertext? What operations do they perform? Well, the set of operations used by any encryption algorithm are a combination of either, or can use either substitution or transposition, or a combination of them. Substitution is when we take some element of the plain text and replace it with another. So we substitute one with another. Transposition is when we rearrange elements in the plain text. If my plain text is ABC, substitution is if I take that plain text and produce, if I'm using the entire alphabet, substitute the letter A with the letter G, B with E, C with Q. That's an example of an encryption algorithm where we're substituting one element in the plain text with some other element from some language. In this case, the language was the English alphabet. Transposition is when we rearrange those elements. Just mix them in some defined way. And we can combine those two operations and have multiple stages. That is, we could have an encryption algorithm that involves replace these letters with these letters, a substitution, followed by a transposition, followed by another substitution and a transposition, and so on, such that we get a much more complex encryption algorithm, and that the resulting ciphertext, it's hard for the attacker to find out the original plaintext. We'll see that concept as we go through different algorithms. They use the two basic techniques, substitution, transposition. Another way to characterize different cryptographic systems is the number of keys used. We've briefly mentioned that. A symmetric key encryption system, the sender and receiver use the same key. It's also called single key or secret key encryption, shared key encryption, or conventional encryption. It's the original type of encryption developed. It's been around for thousands of years. An alternative, which we'll eventually look at, is public key encryption. The sender and receiver use different keys. We refer to as asymmetric encryption. That was developed not so long ago, tens of years ago. We're going to focus on symmetric for now. Another way that we classify different ciphers is on how much plaintext they operate on at a time. And we can talk about a block cipher and a stream cipher. Basically, a block cipher takes a block of, say, 64 bits or larger of plaintext, encrypts, and then takes the next 64 bits or larger and encrypts. It takes a block of data at a time and encrypts. Stream cipher operates on smaller elements, 1 bit, 1 byte at a time, and encrypts continuously. The main difference is in the speed at which the algorithms are implemented. Normally, a block cipher is implemented to be efficient for large blocks of data, megabytes, gigabytes, and so on. A stream cipher is normally implemented to be fast when we have a continuous stream of data, like a voice call. If we want to encrypt our voice call, where we're talking, and with voice, I'm talking on a Skype, and I want that encrypted across the internet, I'm generating a stream of data. I would use a stream cipher to encrypt that and send it as it's generated. If I have a 1 megabyte file, my exam that I want to encrypt, I would normally use a block cipher. They differ mainly in terms of implementation aspects. We're going to look at symmetric block ciphers for the next lecture or two. Let's look at a cipher before we look at attacks. We'll come back to these slides. Let's look at some substitution techniques. And the first basic cipher, the Caesar cipher. In substitution techniques, if we think of the language of the plain text is the English alphabet, it could be a different alphabet. It could be the Thai alphabet. It could be numbers. We define it as the English alphabet. Then we take some plain text letters and replace them with others. We substitute with others. Let's see an example. The Caesar cipher, known to be used by Julius Caesar 2,000 years ago, we take, if we use the English language, we take a plain text letter, and the output ciphertext is that letter shifted by 3 positions. Here's our potential plain text inputs and the corresponding outputs. What is the ciphertext if that is the plain text? VW input plain text S, output ciphertext V. Why V? S shifted by 3 positions. That's the original Caesar cipher. Shift 3 positions along. And same for the subsequent, for the other letters. We just take the next plain text letter, T, and the output would be the letter shifted 3 positions along, which is W, and so on. Very simple. We've replaced input plain text letters with output ciphertext letters. And this is our ciphertext. We send that across our network, our recipient receives it, and they decrypt. And the decrypt is simply the opposite in this case. Go back to the left 3 positions. That is, receive W, go back 3 positions, then the plain text will be T, given here. So we'd get the original plain text back at the receiver. What's the key in this case? The number of positions we shift. The original Caesar cipher we shifted by 3 positions, but in general we can say we can shift by K positions. Let's change the cipher so that we don't shift by 3 positions, we shift by 2 positions. Then this is with K equal to 3, with K equal to 2. What's the ciphertext? Next. That is, take S, shift by 2 positions, U, T by 2 positions, V, E becomes G, and so on. So if we shift by 2 positions, this would be the ciphertext. If we shift by 3 positions, this would be the ciphertext.
And the positive or negative driver for shift right or shift left or not?
We wrap around, and we'll see that mathematically we use a modulus. That is, if the input is Z and we shift by 2 positions or 3 positions, we come around to C. So if we look at the letters, the way to visualize it is we wrap around in the shift.
Can we shift left by negative number?
We could define an encryption cipher to shift left, but in fact, that's the same as shifting right a different number of positions because it wraps around. Yeah. So, in the general Caesar cipher, where we can shift any number of positions, the number of positions we shift is the key. Okay, so if I have my plaintext message, I know the key, 2. I create this ciphertext, I send this ciphertext. The recipient must also know the key, k equal to 2. And if they know that, they can easily get the original plaintext back. Because the recipient knows, okay, this was obtained by shifting 2 positions. I'll just shift it back 2 positions. U will become back to S, V to T, and so on. What about the attacker? What does the attacker do?
If we know the key, we can reverse.
The attacker doesn't know the key. That's an assumption we always make. Initially, they don't know the key.
Use the frequency of method.
Brute force is easy in this case, or we can do some more intelligent analysis and use some, we'll see later, some frequency of analysis of the frequency of letters. Brute force attack is try every key. How many keys are there? 25 or 26. 26 in theory, 25 in practice. What if I use key equal to 0? What's this ciphertext? Not so smart, that key. All right, it's a key. So in theory, there are 26 keys. Because we wrap around, k equals 0, 1, 2, 3, 25, k equal to 26. If we take Steve as an input, take S, move it 26 positions, k equal 27 is the same as k equal to 1. So in fact, we can shift an infinite number of positions. There are only 26 different keys here. 26 different combinations of ciphertext that we can produce for a given plaintext. So what the attacker can do is what's called a brute force attack. Take the ciphertext that they received, they don't know the key, try every key, all 26 of them. And from that, look at the output plaintext, the 26 different plaintexts. One of them should look like an English word. The other 25 should look like random characters. And that way they can discover the plaintext and the key. That's our first cipher, the generalized Caesar cipher, shift by k positions. Mathematically, we can express it like this. Encrypt, take, if we map the letters to numbers, A is 0, B is 1, Z is 25. Then mathematically the encryption is this equation. Take the plaintext plus K, which is the number of positions we shift, mod by 26, this is implementing the wraparound part, and we get the value of the ciphertext as a number, and we can map that number back to a letter. And similar for decryption. How many letters in the Thai alphabet? 44. Can you use the Caesar cipher for the Thai alphabet? let's say you have just those 44 characters. Then you could write an equation which would be the same. We just, instead of having 26 characters, we have 44 characters, and we just shift by k positions. Mathematically, it would be encryption is p plus k mod 44, the length of the alphabet, and other alphabets as well. What's next? So, that's our first and very simplest encryption algorithm, mathematically expressed here, and the corresponding decryption algorithm. Plain text and key is input, ciphertext is output. Not very secure, because an attacker can easily do a brute force attack. We have 26 possible keys. Just try them all. We need to have more keys possible so that the attacker cannot try them all in a reasonable amount of time. Not very secure from other reasons as well. Even if we don't do a brute force attack, we can break this cipher. Let's see if we can show an example on the computer. That's, if you can read it, that's some ciphertext generated from a Caesar cipher. What does it say? A generalized Caesar cipher. Well, no. You need to, what you would do is try all possible keys, k equal to 0 through to k equal to 25, and decrypt, and you'll get different plain texts. It's not in the lecture notes. It's a new one. Let's decrypt it. Let's do a for loop with I or k, I in. For k in 0 to 25, and get this, print out the key, echo the key, and then apply some cryptography algorithm, Caesar cipher, decrypt. What was our ciphertext? I've got to get this correct. Simply, it's going to, doesn't look so elegant here. This is a piece of code that applies the Caesar cipher, decrypts this ciphertext using key k, and we put that in a for loop where k is going to be 0 to 25. And it's printing out the key and the corresponding plain text. Tell me the key. It's trying all. Okay, so we've found the key. So by trying all 26 keys, we got 26 different plain texts, possible plain texts. This is important. For this brute force attack to work, we need to be able to recognize, of those 26 plain texts, we need to be able to recognize which one is valid. We can, because we assume that language was English. If the message was originally in German, Some of you may not have got it, or in some other language. We assumed it's English, so we can recognise which make up English words and which don't. And this is the only one, meet in lobby at 10, that makes up English words. All the rest look like random characters and don't make words. So for a brute force attack to succeed, try all keys, be able to distinguish which of all possible plaintext is the valid or correct one. We can do that there. Now we have the key. Let's try a more intelligent way to attack this cipher. Yes, we can do brute force, but it means trying all 26 keys. Can we be a little bit smarter so that we don't have to apply 26 decryption operations? And how do we do that? We had an answer before. How can we do a smarter attack, cryptanalysis, of our cipher without trying all possible keys? Again, see the repetition of characters. In any language, the language has structure. And therefore,
every language we have statistics about how frequent each character appear in general text.
yes, because the language has structure, therefore some characters appear more often than others on average. The letter E is much more common than the letter Q in English text.
Yeah.
Okay, if you take a large piece of English text, and in fact, if you look at many pieces of text in English, you can get the approximate statistics of which letter is the most frequent. And not just single letters, but also what's called digrams, pairs of letters. The letter TH, the pairs TH, IN, ON, those diagrams are much more frequent than QZ. Using those statistics, we can do some analysis of the ciphertext and try to discover the key that way. Let's demonstrate that. Sorry. So I've found an online book, an old English book. Let's explain. An online book, I've saved it as a text file. So it's just, I don't know, it's got 44,000 characters, English letters in there. I'm going to count the number of letters in that book and sort them and rank them in order. Of the 447,000 letters, 12.29% were the letter E. Then 9% the letter T. This is just the top 15. There is another 11 not shown. So the least common ones are not shown here. So it ranks in order of the most frequent letters in that large text of English. And that is close to what you get in many texts of English. E is usually the most common. Maybe it's not exactly 12.29%, but it's usually much more common than the next letter. Now let's look at our ciphertext. Which letters are the most common in our ciphertext? Sorry, I get this right. We've got a different ciphertext this time. I'll show you the ciphertext. There's our ciphertext, so a bit longer. And now let's count the frequency of letters in the ciphertext. the letter J is the most frequent in this ciphertext. 10%, Y 8%, and what do you think the key is for this Caesar cipher? I'll go back. So here's of the ciphertext. The most frequent letters are J, Y, N, and there's more. And of our English language, or our example book, the most frequent letters, if we scroll up, E, T, so given the frequency of letters in the English, we'd expect these letters to be most frequent in the plain text. Maybe not the same, but we'd expect the plain text to perhaps the most frequent letter to be E, and then T and A, maybe in a slightly different order. But what we've got in the ciphertext is J, Y, N. Does that give us any information? What information? What's the answer? Key, what's the key? Why 5? What's the letter E? E is letter number 5. And J? J? J is the letter 10. That suggests that the ciphertext was generated, we knew it was a Caesar cipher, it was generated by taking all our letter E's in the plain text, shifting them by 5 positions and getting the ciphertext letter J. Because down the bottom here in our ciphertext, 10%, the most frequent letter is J, most likely that corresponds to the most expected, or the letter expected to be most frequent, which is E. If that's the case, then we used a key of shift by 5 positions. What about T and Y? Does that make sense? T would be character number 20, or is it 19 if we start from 0? 24, I think. That one matches as well. From looking at the first letter, J and E, we had a guess that the key was 5. Let's try that guess. Let's try our first guess first. See if this works. We start at 0, do we? Ah, okay. What's T? What's T? 20, I think. You'll confirm. We just decrypted our input ciphertext, that was the ciphertext before, using key 5, and this is the plain text we get. This makes sense. That is, it's some English words. And that's found the key without trying all possible keys. This is just a course description.
Can you read for me?
No.
Next time I will send email to you like this. And I will give the key.
The point to finish on is that we've seen two types of attacks. Brute force, try all keys. Works if we have a few number of keys. But will not work when we have stronger ciphers with large number of keys. Second attack, cryptanalysis. Use some structure of the ciphertext and plaintext to work out what the key should be. And in that case, we worked out with just one decryption. We tried one key. That was successful. Tomorrow we'll finish on the attacks and go through other ciphers. See you then.